So we have 3.2 lesson, and this is all about solubility. And when you were doing net ionic equation in intro level class, you talked about some salts that were insoluble, but you know what? That was kind of a lie, because in truth, everything dissolves a little bit, at least salts and rocks and so forth do. And that's the reason that we have a Grand Canyon, because those rocks over the last 100,000 years or whatever didn't all tumble end over end and end up in the Gulf of Mexico. Mostly they dissolved into the river. So we're going to talk about the fact that these salts that we used to call insoluble actually do dissolve a little bit. And sometimes it's a very little bit, but they do dissolve to some extent. And here's our standard form. Now remember that when a solid ionic compound breaks up and dissolves, it becomes aqueous plus and minus, however many plus and minuses there are. And we can make a K out of that. And again, it's the same products over reactants to the power of the number in front kind of thing, except that the reactant was a solid. So the denominator becomes essentially 1, and it, for all math purposes, disappears. So why don't we try example 1? So the molar solubility is this much. Now, I would take a note. What they mean is that this is the amount of this that can dissolve. This is the maximum amount of this overall that it can achieve. It can achieve this molarity. Now, here's the thing, though. When this dissolves, we get 1 sulfate and 2 silver ions, as we see here. And they do expect, by the way, that you're going to be able to write this out. They're not going to hand you the products of the solubility reaction, the dissolving dissociation reaction every time at all. They're going to expect that you can figure this part out. So stop and have a think if you need that. So when 1 of these dissolves, we get 1 of these and 2 of those. Now, for some reason, somebody has decided that S is preferable to X. It doesn't really matter. You can choose any letter, of course, but we get 1 of these and 2 of those, where in the first place we had 0. So at equilibrium, we settle out to one of these and 2 of those. So the KSP will use the coefficients as the exponents again. And it seems a little bit odd, but this is the molarity, but the K depends on the molarity, but then uses the the coefficients as the exponents. So this 2 does double duty here, and it becomes this multiplier, and yet again this exponent. And this happens a lot, that we end up with this sort of, in a sense, standard form, and we get a total of 4s cubed. But we know what S is. We know how much this can dissolve. We know the molarity it can support. And so when we get 1 of these dissolved, we get 2 of those and 1 of those. And so however many you dissolved of these, you also get the same number of that. And so then we get 2 of those. Well, they didn't rewrite it out. I was looking for them writing it out. But essentially, so we get S cubed and 4 multiplied by that. Now, K then will be that math all rolled up together. Cube that and multiply by 4, and that is KSP. So if you made a 0.1 mole solution in 1 liter, you would have 0.01 mole. So if you had 0.01 moles in 1 liter, you would have 0.01 molarity. What will that look like? Well, it can support 0.0229 molarity. So it can support more than you've done, so everything will just stay dissolved. And if you want to pour some more in, it'll dissolve that too. I mean, not a lot more, but some more, certainly. So what will it look like? It will look whatever color that dissolved set of ions is. Often it's clear, but sometimes it's not. And it will, all of it will dissolve, and you won't get a precipitate. What happens then if you try 0.04 moles in a 1 liter solution? Well, you've set up this molarity, which is greater than the amount that can truly dissolve. So if somehow you manage to pour this many, this molarity of ions in there into 1 liter, you'll try to set up a molarity that is impossible, because it exceeds the maximum amount that this can actually create, which means then you will get the reaction running backward, because this and this in the K-math creates a number, it creates a Q that is too large. And to settle out to equilibrium, it will have to produce a solution where the K value is true and your Q is too large, so it'll have to run back to the left, and you will get a precipitate. So what's the concentration the products, I changed this because that's actually what they asked down here. They had a conflict between what they wrote and what they solved for. So they give us a K, and we know that these are the products because you get 2 of these. Oh, excuse me, that's mercury. Mercury, by the way, has a very odd habit of sticking together in pairs when it's +1 each, so that it's +2 total. If your intro teacher never mentioned that one, I understand, but it does. Mercury, Roman numeral 1, +1, occurs in pairs for reasons that was never told me, but there you go, it cropped up. So we get 1 set of the pair and 2 of the chloride ions. So we get 1 value of S and double the value of S for however many this dissolves. So again, we get 4S cubed, and we know the K value there, so we can solve for S. Now, this brings up, how do you take an nth root? Because I assume you have a square root button on your calculator, but do you have a 3rd root? And do you have a 4th root? Now, you may need to go on YouTube or talk to your teacher or something, but I'm telling you that the other version of square root is to the 1/2 power. The 3rd root is the 1/3 power, or 0.33333333. We'll just stab in about 5 or 6 of those and it'll be good enough. You'll exceed the significant figures. And the 4th root would be something to the 0.25 power. So what we can do here to solve for S is divide by 4 and then take the answer to the 0.333333 power, and you will solve for S. What are the concentrations? Well, that's the mercury pair concentration, just S, but the chloride ion concentration would be 2S. On the backside, we have a bit of a discussion about what solubility means, because a greater KSP does mean that something dissolves more, but that only really is useful and a valid comparison when you're using salts that create the same number of ions. These were very deliberately picked so that they do not produce the same number of ions, because we're going to get 1 of these and 3 of those, and 3 of these and 2 of those, and 1 of this and 1 of that. So when we solve for the molarity of the dissolved salt, we're not going to use the same math at all. So the molar solubility is going to have a very different kind of calculation, because we're going to have 1 of those and 3 of those to the 3rd power. Remember that we're going to have 1 of these and 3 of those, so this 3 here actually becomes the coefficient in front. And that's why we have a 3 in here and yet again an exponent here. If you don't know what I'm talking about, hit pause and write out the dissociation reaction here. Write out this dissolving, so you get 1 of these that's a +3 and 3 of these that's a -1. Then when we set these maths equal to the Ks, we solve for S, and that's the molar solubility for each one. And it turns out that we didn't predict the real solubility just by glancing through the K values. So this example is the kind of thing that would come up on the test, and something even more complicated really than this on the test. So hit pause and give this a read. This can be a bit tricky. So we have this much of a solution of calcium chloride, and the chloride ion is this much. Okay, so we have this molarity of this much of silver nitrate. Now, will a precipitate form? Now, you are supposed to know that a nitrate salt is very, very soluble, and they're telling you that they dissolve this. Now, I went and double-checked my solubility rules, and this is a soluble salt. But they told you it's already dissolved because it has a chloride ion concentration. So whatever amount they're using is aqueous, and so you don't really have to go look at that, and there is no solubility chart provided. But you don't need one because they said it was the chloride ion concentration. So this was already dissolved as much as they wanted, at least. So here's my point, though. You combine these two and you have a possible double replacement reaction in your aqueous solution. Now, we have 2 possibilities when we trade the partners. We can have this or we can have that, and we're supposed to know that this one is right out. There's no possibility of forming that. The only one that is even possible is this one, and your giant clue is they gave you a KSP, and in fact, the KSP is really low. It's 10 to the -10. I mean, this stuff is not very soluble. So can there be a solid? Oh, yeah. Now, will there be with this concentration provided is the question. There certainly can be. It wouldn't be hard to do, but did they provide enough ion to make it happen, or did they provide so little that it will just stay dissolved? That's what we're trying to find out here. So we can take the molarity and multiply by the original liters, and that will cancel out the liters hidden in here, and then divide by the new liters. Remember, we have a new amount of liters when we add these up, and we get the new molarity. Now, I think of it like this, in case you care. They are right, though, that the milliliters will cancel out. So if you're good at math and you can, you know, keep track of what you're doing, obviously this will work, and we get a molarity. For the Ag+, we also get a molarity, the same math. And now we know the molarities of each of the component ions of our possible solid. Let's find Q and see if it is K, because I bet it's not. When we put these in, products over reactants to the power of the number in front, except that our reactant is the possible solid according to this dissociation reaction, we're going to see if this thing wants to run back left. So when we put in the molarity values here, right, what do we get? We get a Q that is this, which is bigger than the K value. Q is bigger than K. I mean, Q is bigger than K. We have too much product to support it. This kind of salt in water, at this temperature at least, cannot support the molarities that create a Q of this value. It can only support them up to where Q reaches this value. And remember, this is a smaller number than that one. And so some of it is going to have to run left and become a solid to get the K value to be true, get the Q value down to where it is actually K, and you will see a solid form.